We also notice that unlike in the previous picture that we showed, where there is abrupt saturation, the actual saturation of the flux is not abrupt, and therefore we cannot model it by a piecewise approximation. However, we have looking at view graphs, explanation for that, because we have a reluctance concept which shows us that we don't have an abrupt saturation of the core material. In other words, the core starts saturating from inside out. So even if you assume the piecewise linear approximation for a BH characteristic, we'll still get a relatively smooth and curved flux versus ampere turn characteristics, because this is an integral effect and the core starts saturating from inside out and resulting in eventual smooth characteristic as we see on the scope. Let us now look at some saturation effects in more details and how the saturation is affected by the various parameters in the circuit. Here we see that by driving the core very hard, the volt-second balance will result in a flux linkages which are still triangular linear because the voltage is square wave. However, reflected through the nonlinear flux linkages versus the current characteristics shown in red will result in the current drawn from the source, or current in the winding, which will be highly nonlinear, and the more so, the higher it is on the knee of this characteristic. We can see this effect on the screen showing the time domain waveforms, where we have a top trace showing the flux linkages and the bottom trace showing the current in the winding. And we see the saturation effect. As a matter of fact, each time you observe that the inductor current in switching converters shows this spiky behavior, that is the first indication that the inductor was either not properly designed or it is for some other circuit reasons driven into saturation, which of course in many applications needs to be avoided. Now we can look at how we can get out of this saturation mode by, for example, increasing the switching frequency. As we see on this domain, we reduce the flux swing, and therefore the flux excitation are reduced in magnitude and corresponding current excitations are reduced in magnitude. But notice that in the same time the current spikes are eliminated, and in fact more and more linear waveform is observed. Of course, that is because if you look now at the BHLoop characteristic, BHLoop characteristic is now of flux linkages versus current characteristics contained to the smaller portion where it is still in a linear region, and therefore both flux and linkages and current are linear waveforms. Now let us show again, if we go now back to our original 40 kilohertz switching frequency, and if we now start driving the core with the voltage source, increasing the voltage source, we again can get into saturation, as we see by this spiky behavior. What is interesting to point out now, as we see on the view graph, that ideally, if we had the single-valued magnetization characteristic shown in the red, then we would expect that in the saturation we would get the current waveform which is symmetrical. However, knowing that the BHLoop characteristic of the core is double-valued function, the driving the core in one direction will go along the characteristics in this way, and then de-exciting the core will go along the characteristics in the upper trace. Therefore, the two parts of the curves will not anymore be symmetrical, and the unsymmetry is actually due to the finite width of the BH loop, and it's in fact reflecting the presence of the hysteresis loss current in a device. We can see actually and observe that in the scope, that if you look at the 50% driven converter, that basically the outgoing and downgoing curves are not identical. And as we said, due to unsymmetry is due to the finite width of the BH loop.